Okay, so we can now you can see the ratio, that how many ratio we can find. Now the second things we need to learn here, that if we have this ratio, like this is considering when we did a math, the measurement conversion, correct? We have some standard value. So similarly here in the context of the chemical equation and ratio, for this reaction, this is the balanced established reaction for the production of ammonia. And here we have the ratio, and this is very standard. So now we know the ratio of nitrogen and hydrogen is actually 1:3. That means if we use the 1 mole nitrogen, we have to use the 3 mole hydrogen. So now if we ask you, by changing any kinds of molar ratio of any ingredient in this reaction, we can calculate the amount in the context of this standard ratio, correct? So that means this ratio actually will be using as a conversion factor. Okay, so now let's look into some example. So this is the biggest, little bit of bigger chemical reaction. This is actually called the, you don't need to be remember here anything, you just need to understand. So this is called the calcium apatite. This is kind of complex that, you know, used in the toothpaste. If you see here is fluoride, so that helps to clean our tooth or something. But we will not go this way. This is just a chemical, balanced chemical reaction. We need to see the ratio. If you see this compound and the sulfuric acid, so calcium apatite react 1 mole calcium apatite reacts with 5 mole sulfuric acid to produce 3 mole phosphoric acid, 1 mole hydrogen fluoride, and 5 mole calcium sulfate. Now if you look back, this is not complicated, no need to scary. So many ratio we can be right in this context, correct? Because we can write the ratio between here, we can write the ratio between here, we can write the ratio between here, we can write the ratio here. Let's change the color. Then we can also write the ratio to calcium apatite to here, same to here, same to here. Now we can also make the ratio, so many we can do, I mean on the basis of our need. So we can make the ratio here, we can make the ratio here with that, even we can make the ratio here, we can make the ratio here. So that means so many ratio we can make it on the basis of our need. Got it? Now you could see this kind of complicated chemical reaction, I mean bigger size the reaction and the example and the ratio. So I hope you now got it that how we can make a ratio knowledge or quantitative knowledge from the balanced chemical reaction, and we can calculate the amount for any other ratio or context. So now go for the calculation. So this is the same reaction that we saw in the last page. Let's see two examples. Calculate the number of moles of phosphoric acid. See what we have to find. Let's think easily. We have to find mole of phosphoric acid formed by the reaction of 10 mole of sulfuric acid. Now we have to find the phosphoric acid formed for the reaction with 10 mole of sulfuric acid, but we know what we have the standard information. What information else we have in addition to that? So we will write this chemical reaction, or we will provide you the balanced chemical reaction. So now you need to look into the ratio between phosphoric acid and sulfuric acid, correct? So if we now, let's look into the ratio between the phosphoric acid and sulfuric acid. So what is the ratio between the phosphoric acid and sulfuric acid? See, look into here. So 3:5, correct? So the 3:5, I mean 3 mole phosphoric acid divided by 5 mole sulfuric acid, this will be our conversion factor. Now you can ask me why phosphoric acid in the top, because we already learned our rules that whatever the unit Our target calculation we have to find out always right on the top. And then in compare, we will write the down. So see, this is also actually the conversion factor, but the difference is that in case of measurement like gram, kilogram, pound, meter, mile, whatever we did, we already have established in the formula. But here we have to find those standard information from the balance chemical reaction. So now it is very important that when you do this type of calculations, you need to first make sure that you didn't do any mistake to balance the reaction. Because if you make a mistake in balancing the reaction, your whole math will be wrong, correct? So this is important. So now here we have our conversion factor. Let's write. And what more information we have? We have 10 mole of sulfuric acid. So we will multiply the 10 mole of sulfuric acid with this content. So next we will find this mole existing unit will be nullified, and then we just need to be calculated and we will find the amount of mole of phosphoric acid we need to produce this mole of sulfuric acid. So that means from the balance reaction, we saw that 3 mole phosphoric acid can produce can be produced from 5 mole of molecules or moles of sulfuric acid. But they are asking you not for the 5 mole sulfuric acid. They are asking that if you have a 10 mole sulfuric acid, how many mole of phosphoric acid you can produce? Frankly speaking, this math is very easy. How? In that sense, you don't need to do anything because for the 5 is 3. So for the 10 must be 6. But we cannot guarantee that we will always have the easy calculation, correct? So that's why we need to know the procedure that how we have to do that. We have the another example here. Calculate the number of moles of calcium sulfate formed by the reaction of 10 mole of calcium apatite. So now you have to find the ratio of calcium sulfate and calcium apatite from the balanced chemical reaction. So if we look back here, the calcium apatite and this is the calcium sulfate. See? Okay. So here we go. This one. So we can see here the ratio between the calcium sulfate and this molecule is 5:1 because we have to find calcium sulfate, not this mole. So that's why we will write the mole ratio between the calcium sulfate and calcium apatite. So 5:1 in context to molar molecules. And we have 10 moles of calcium apatite. So we will multiply with that. So this unit and this unit will go nullified. So we will got our answer. So that was the one thing. And I wanted to show you because this is our rules, how we do. So I think now you guys will be very okay if you have some example. Yeah, I think you have some example. So when we will do that. So this is just the review from the from the last topic we discussed. So we have that very important topic today, so I do not want to take more time there. So now I think you can calculate any kind of math related to here. Yeah, so please check it out, your math and the balancing equation related question. I didn't delete anything. I keep all the questions with answer that normally we use for making your exam question. So practice it. And maybe you noticed that I try to keep the question pattern according to the lecture. I changed a little bit. So do not memorize the lecture, try to understand. Yeah. So energy consideration. Just yesterday, I think I was talking that the way energy never destroyed. It transfers from one to another. Like today, if in this room have, I'm not sure AC is running on or not. So what AC will do, AC will extract all the hot air from this room and AC will transfer it outside. Similarly, now we can see that this room, if we consider that this is as a system, so if we see all the windows are now closed, all the doors are closed. So obviously the temperature inside the room and outside the room is not same, correct? But at the same time, now if we try to open the window, what will happen? Some of the inside temperature will go outside and outside temperature will come in. And the temperature will go out and come in until it's saturated and balanced, equal, right? So this is the thing that the energy in the form of heat, in the form of current, in the form of temperature, whatever we think, never destroy. It just transfers from one to another. So in that case, we have this chapter and our first topic is here the kinetic and potential energy. So normally energy are categorized into two broad sense called the potential energy and the kinetic energy. In very general sense, I want to say potential energy is the energy that already stored in one position. And kinetic energy is a kind of translation of potential energy. For example, now I stand here. If I need to work, I need to expend some of my energy. So when I am working, this is my kinetic energy in motion. But when I am standing here, I have some energy stored. This is my potential energy. Second example I will give you. When we will, our elevator is very slow, correct? So sometimes, yeah, 5 minutes takes actually here. So when our elevator gets very slow, what we do sometimes, either stare up or stare down. Stare down is easy, but up is not so easy, correct? So stare up to down in a motion, correct? When we go. But this is also very natural phenomenon because of the gravity. Like if you go for the mountain to high, when we will walk from high to down, it's very easy, like stare up to down. Because of the gravity, it is very natural. But if we want to go down to up, we need to apply our own stored energy. So the own stored energy, that's the potential energy. And whatever the energy first we have and then we in a motion and translate it into work, this is called the kinetic energy. And you can see this is the potential and in motion, this is the kinetic energy. And here, I want to say something in addition to here. If you look into the equation, potential energy, mass, gravity, height. So that means potential energy is proportional to the mass, gravity, and height. So if the size is bigger, that means obviously they have the energy stored is more than the thing. So if it is go up, then so up, the energy will be high. It's very simple that if a leaves from the tree fell down, the effect on the road, and same height, if the meteorite or rock something fell down, it's different because the rock mass and the tree leaves mass is different, correct? It makes sense. So this is the relationship for the potential energy. And in case of kinetic energy, half mass and velocity square, because this is the we find by doing the investigation. So this is our equation we can keep here, that the whatever the mass will be translated into energy and the velocity. You remember nowadays so many modern toys for the kids, but when not we, I think when you guys were kids, there are some mechanical car. You know the mechanical toy car, we use some lamp and also like that type of car. Let's consider this is one toy car. In childhood, I think it's still available. If you just move like the wheel and you just do that, it will go some distance. If we do more and do, it will go more distance. Even the ramp, child use the ramp, go. So it depends on how force and velocity you start it. Correct? Then it will go that distance. So this is the mass and velocity is the kinetic energy. So this is our two kinds of energy that we normally use in the chemical reactions also. So the potential energy and kinetic energy. So potential energy, that is, we can also call the stored energy and due to position. And the kinetic energy is related to the motion. So next move on. Yeah. So as I say that if we can consider that this room as a system, in the chemical reaction, system and surrounding. So if we consider this room, let's consider this room as a test tube or chemical beaker where we will do the chemical reaction, correct? So system and out of system or surroundings. So in a chemical reactions, we will always use or define the chemicals themselves as a system. So that means reactants or products, they are the system. And except reactants and products, other everything are surroundings. For example, the solvent, glass oil, and air. So then please make sure the system is in case of chemical reaction, because our total focus on the chemical reaction. We will not be talk here anything in the context of physics or that in those things. Like I also sometimes teach the thermodynamics in general chemistry second part, that mainly take by the senior students and the other high grade students. I also have some recorded lecture, but that's will not helpful because that's a more depth. So we will not go there. We will talk today here only on the behalf of reaction. And we already know the exothermic reaction and endothermic reaction, correct? Endothermic reaction are from when bond break. Exothermic reaction when bond form, new product. So we will keep our talk limited to there according to our syllabus. So let's move on. So it's okay. Energy conservation. As we now know, just like there is a fixed amount of mass in the universe, there is also a fixed amount of energy that I just mentioned yesterday, and also we now know. So energy cannot be created nor destroyed. This is called conservation of energy. And last time during the chemical reaction balance, we also learned the conservation of mass of conservation, correct? Law of mass of conservation in the context of the chemical reaction. And here, in the context of the energy, we also know that energy cannot be created nor destroyed. Energy can be transferred from one body to another. Here I want to say something. During the winter, when we go outside in the negative or minus temperature, if we don't wear the gloves or something, sometimes our hand try to come and hold. But if we come inside the door, if we hold somebody's hand who is staying inside, then what happens? Your cold temperature will transfer to the hand of the hot hand, correct? So that means that energy can be transferred from one body to another. So that's where trying to say that energy can be transferable, but energy cannot be destroyed. Let's see here now. Exothermic reaction and endothermic reaction. Okay. Let's consider solvent is our surrounding, system our chemicals. Now, endothermic reaction, energy transferred into the system. Into the systems means chemicals, and the chemicals means reactants. Are you guys clear here? Yes. Now, exothermic means energy transferred out of system. So that means when new compound is forming, then they also leaving some energy in the form of heat, in the form of light. So this is the out of system. That means those heat or those light is going to the surroundings. Like when you will go into the lab, hopefully in the next semester or near future, you will see the some reaction. When we run some reaction, it depends on the exothermic or endothermic. So if this is the endothermic, we need to apply some heat. When the reactants absorb those heat, you can feel the beaker very cold. In the same, in the other context, if the reaction is exothermic, they will release heat. So you will feel sometimes the test tube bottom is getting hot, or the beaker is getting hot. So that means the energy will be out into the surrounding. As you all know that now what is the system, what is the surrounding. System is our chemicals, reactants or products, and surroundings other than chemicals, everything is surroundings. Like if we just talk in terms of the thermodynamics or physics, that this room is a system and outside everything is surrounding. So like that. Now potential energy of the system increases here. And in case of exothermic, the potential of the system will be decreases. Decreases in that sense because they will form the new compound and they will release the heat. So they will not have anymore. That's why the total potential energy will be decreases in case of exothermic and increases in case of endothermic. You guys can note it down because this type of little things sometimes make confusion. So for the beginner, so if you note down, it will be helpful. Like here, endothermic reaction. In case of endothermic reaction, now what is the relationship between the total potential energy of the system? So this is our relationship. So the total potential energy change, we can do like the del PE equal to potential energy products minus potential energy of the reactant. So if we do these two energy subtract, so whatever the result we will get, that must be greater than 0. So that means you are going to find the potential energy or the potential energy change, whatever you say, the system will be greater than 0. That means positive. Okay. And in case of, because see here also, in case of endothermic reaction, because we know that these are the reactants and these are the heat, we need to initiate the reaction. So these are the endothermic reaction, the system is absorbing heat from the surroundings. That's why when surrounding giving the heat to the system, obviously surrounding lose energy in the form of heat or something. So that's the main thing is here. And in case of exothermic reaction, since the system releasing the energy in the form of heat or something to surroundings, that's why the del P will be less than 0 and the total del PE and this is negative. Now, before going to here, I will draw something that will be little bit of, okay, I will draw here or later. Okay, let's see, go back to draw something. This is just to understand. So sometimes when we talk about this potential energy for the endothermic and exothermic, as we just see the overall potential energy difference in case of endothermic is positive and greater than 0, and in case of endothermic and exothermic is negative. So now we can always use this type of potential energy in the context of reaction diagram. So let's consider this way is a potential energy. And this way the reaction context or whatever we say during the run any reaction. So now let's consider for the exothermic. I'm giving here time little bit. I'm taking because if you have this clear basic, this chapter is very basic, so you will be very familiar what you have the math problem or the question solution. So this is the exothermic reaction. Let's consider this is 0, this is 100 potential. Let's consider this is 200. This is just example. This is not the exactly graph. Let's see, this is 600. So whatever we have. So let's consider here. This is reactance. This is called the transition state. I will explain here, don't worry. And this is called the product. So this is for the exothermic. We know the total potential energy. We just learned that the potential energy of product minus reactants, correct? So now, in case of exothermic reaction, see here, this is, we will count the potential energy. Let's consider this is 100 for product and reactants for 200. So now I think the mathematics is very clear that why this is negative is come. So this is less than 0, this potential energy in case of exothermic. Now let me little describe what happened during the chemical reaction. As we know that any kinds of reactants we start, first they broke their bond, correct, old reactants. And when they broke their bond, final the balancing of chemical reaction only show the reactants and product, correct? They don't show here transition state. So the old bond is broken, and then they try to making the new bond, and then finally they produce the product. So between the forming and breaking the bond, the stage we have, this is called the transitioning state. Now, in the chemistry language, there is one thing we always say, the activation energy. So activation energy means, as I say, that if I stand here and if I now want to move, I need to apply minimum energy. So similarly, any kind of reaction to proceed, you need minimum energy to run those reaction. Like two reactants will break the bond, they still need some energy. Two reactants will break bond and then will come close, they still need some energy. So those energy is called the minimum energy to run the chemical reaction. This is the potential, activation energy, and this stays after breaking the bond and making the new bond, new compound. All those things happen in the transition energy. So this is the basic energy diagram, very common and very standard energy diagram for doing or explaining the exothermic and endothermic reaction. So this is for the exothermic reaction diagram, how it is happen. I'm not going too detailed because this is not in your syllabus. I just explain here so that you guys can understand easily when you will do the math, why it is negative, why it is positive. Now, let's delete the notation. It will be recorded, so don't worry if you need. Now, similar kind of graph, the potential energy versus the reaction contact reaction for the endothermic. Here, writing with the mouse is difficult. So what happened here? As we know, that is for example, maybe the 0.0, 100, 200, whatever you think. We know for the endothermic reaction, we need to give extra heat, correct? So when we give heat, that means the total energy in terms of heat is high. So the endothermic reaction diagram is like that. This is P. So when we apply heat, reactants or system take those heat. So in case of endothermic, now if you see this is reactant, this is product, and this is the transition state. I'm not going other side. So now if we look into that level, the product energy is more. That's why the del total potential, we know the energy for the product and energy for the reactant. So if we consider, let's see, this is the, yeah, this is the product we have. Oh, sorry, I did a little mistake. That's just give me a moment. I did a little mistake here. Now it's okay. I again try to draw like the exothermic. Yeah, now it comes. Okay. So here reactance potential and go up the product potential. So now product minus reactant. So if we consider, let's see the 300 and the reactance is 200, just consider. Then it will come the 100, that means 0 and more than 1, and this is positive. Why this is more? Because it absorbing heat from the surroundings. This is how. So that's just, you need to be clear. That's why I show this diagram, but this is, I didn't find in your content, but this is from my other content. So please try to be remembered that why the, oh, sorry. Why the positive and negative? We know that now. So we will going back to our job. Yeah, so we are here. Let's now move on for some example. Consider the following endothermic reaction. What we can say about the energy in the system. We just learned here, see, the endothermic reaction, we always apply heat from the outside. So that's why they will be absorbing heat from the surroundings. As a result, whatever the compound they will form, the ultimately the energy difference del E or del PE will be, in case of endothermic, not this one, will be greater than 0. Okay, and in case of another, and you can see the now product and reactant, but actually the main figure is here. You guys can even go to the Google or anywhere. When you will write the exothermic versus endothermic, they will show you the same explanation and the energy diagram curve that I showed. The diagram below represents an dash reaction because heat is. So in that case, heat is upward. So what will happen? Heat is when upward, that time will be endothermic, because we endothermic reaction gain those heat. As a result, it will be upward the product. So if you saw, just remember that in case of endothermic, here, this is the product, and this is the energy upward compared to the reactant. That's why product minus reactant will be positive. That means endothermic will be gained. See, endothermic reaction absorb heat. So the energy of the product is higher than the reactant. Energy is being absorbed by the system. The reaction is endothermic, and endothermic reaction absorb heat. This is actually the theme here, but just for clarification, I try to little more explain there. The heat of chemical reaction, del H. The heat of chemical reaction is due to the making and breaking of bonds. The potential energy of the system change, we say the total energy. We saw the energy for the product and energy for the reactants. So whatever the total energy, that we say the total potential energy, and the total heat of a chemical reaction that comes out, or that happens due to this making and breaking the bond, that also called enthalpy. Enthalpy equal to H. And now if you look into here, so the total potential energy equal to enthalpy and equal to Q. Here, in case of thermodynamics, the term Q means the work. So, as I say, that we have the energy, and when we are in the motion, we apply those energy or heat translated into work. Correct? So, Q means those work. Okay? So, maybe the slide don't have so much detail, but you guys can note it down. Q means the work. That finally we after all those transformation, whatever the things we got, that's called the work. So when heat by breaking or breaking the bonds during the chemical reaction, it translated into work, and Q equal to work. So actually, as a result, the quantitative relationship, total potential energy equal to del H equal to Q. If energy is released, it goes out of the system, and we know that del H less than 0. I mean, same thing, as I say, same thing now will repeat and repeat. If energy is absorbed, it goes into the system, and del H greater than 0, and this is the endothermic reaction. If energy is released, now making and breaking bonds, let's see what we have. If energy is released, it go out of the system, then we know this is exothermic reaction. So in case of exothermic reaction, energy is always releasing in the system. This is the example. In case of endothermic, energy is absorbed, and this is just, as we know, that some of the things we have to be just repeat and repeat to memorize in our head, that endothermic means breaking down and exothermic formation. You need to write little things on your notebook. So breaking down means, see, the kind of okay, dissociation. So like, see, the hydrogen molecule dissociate into 2 hydrogen atoms. But in case of exothermic, 2 hydrogen atoms combine to make the hydrogen. So whatever the things you will see, the breaking down, that's our endothermic, and the formation is the exothermic. Same thing will come in different contexts. Like initially we saw the del PE. See, look back into here, del PE. But we already know that del PE equal to del H, enthalpy equal to Q. So actually the similar type of things will come, but little bit of symbol will be changed because of the context. Potential energy of bond formation. The energy of the HH bond is 436 unit kilojoule per mole. So in that case, energy, just before we saw the product minus reactants, correct? And when we were talking about the energy for the bond breaking formation, we will write like that, del H equal to H final and H initial. I mean, we are talking about for this particular reaction, but the context is the same. So in that case, H initial 0, obviously 0, because before breaking bond, they didn't apply any heat or energy, right? They didn't do anything, like me still. I'm not, if I don't move anything, whatever the things I will eat, every day it will store in my body and I will be fat. So like that, initially the heat is 0. But finally, when they broke out, they find something. So in that case, the del H will be here. And in case of exothermic, the final will be 0, and initially they are taking to break down, they need the energy. That's why this is minus 436, so finally will be positive. So you guys need to know these things. In the atmosphere, there are many single oxygen atoms. Let's solve the question. When these atoms combine to form oxygen, remember that oxygen is diatomic. Yeah, oxygen atom means O. And when we talk about the oxygen is diatomic, O2. Okay, so the potential energy of the 2 oxygen atom. So what will be the potential energy of the two oxygen atom? Because remember, when two oxygen atom combine two oxygen molecule, those oxygen molecule combination of the oxygen molecule, new formation is the exothermic. But the oxygen atom, they are the initial. So in that case, the decreases and energy is released as a heat. Making a bond is an exothermic process. Energy is released by the system and potential energy goes down. So kind of things will come repeat and repeat. And I must say that this chapter is kind of confusion between the exothermic and endothermic. Little bit, not so much. Maybe for some students, not all students. So that's why try to keep review when you do with the focused mind. And as I say that I have the detail of the thermodynamics. For some students, I made it in my previous. I mean the. I don't know here it will come or not. No, it's not coming because I don't, I just made for some student, but that's so detailed that actually will not be helpful. So just focus and nothing else. The two things, exothermic and endothermic. So now you can see here the single bond energy at the table here, average bond energy in kilojoule. So if you look into the bond energy, you will have an idea about the multiple bond energy and the single bond. You remember last time also we little bit of talk about it. So same thing now it will come here. So the positive energy values shown represent the energy required to break the bonds. So all the positive energy, they are showing that those energy required to break the bond, and more energy required, stronger the bond. So here, larger bond energy value indicate the stronger bond. So the larger bond energy, how we will see, look into here, larger bond energy. The triple bond is more high. Double bond is little less than that, single bond. But if this is sometimes, and the length is also high in case of single bond. Bond energy are here. Breaking the bond, we have, that means this is breaking the bond, this is positive, this is endo. And making the bond, del is negative, this is exo. Same thing is coming again and again. And I am also repeating so that it can go into your brain, and that's all, because you just need to do some of exams. The heat of the chemical reaction. So breaking bond and making bond, same thing will tell. So what is the breaking bond, making bond? I will just little bit of show here since we have the example here. See, when we are talking about the breaking bond, see, look into here. We had two molecules of hydrogen, but breaking bond means these two hydrogen molecule actually make by the bond like that, correct? The covalent bond. So breaking bonds means they will break this bond, and that's why you need some energy. Okay, so then when this bond will break, you will have a two more hydrogen atom. So two hydrogen atom two times, so total four hydrogen atom. And this four hydrogen atom will now next make the bond. You guys know very well how we make the covalent bond, correct? So you guys are now getting master on that. So we already know how it works. So then the new compound form, and here the del is negative. The heat of a chemical reaction, overall heat of a reaction enthalpy, is based on both the bond broken and the bonds formed. So now we have some example here. Same thing is coming. Formation of methane. So you can see we broke two hydrogen, as I already explained. This is, I mean, the same thing that I just explained. So we break two H single bond, and we find for this single bond, this energy, since this is the 2 times we had, so this is the energy. We make 4 single bond, so we had the 4, and this is our CH bond energy, so we find this energy. And this is the total heat change in the context of products and, in case of, bond formation and bond breaking energy. This is how we need to calculate. Bond energy calculation. In case of potential energy, we saw the difference, product minus reactant, but here we will see this is our, so this is our equation, the way we will use it. Bond and H broken. So now we have here the reactants and this energy. This is the new bond. So now we are talking not in the context of exo-endo. Now we are talking about the bond breaking and bond formation context. So identify all the bonds that need to be broken. Identify all the bonds that need to be formed and release the energy. Exo and broken means endo. Same, I mean, the value will be coming similar. So in that particular case, we have to break this bond, and also we have to break chlorine molecule. That means, this bond. We will break this bond. See, and this is our energy. And identify all the bonds that need to be formed. So here we will be form the hydrogen and the chlorine, and how many? 2. And this is 2 we will come when we will balance the chemical reactions. Bond energy calculation summary. I mean, the same thing, it will coming. So look into here. And now we have some example. Use the data table to determine the total change of heat for the reaction that occurs when gas hydrogen react with gas nitrogen to produce gas nitrogen tetrahydride. So let's go back to see the job first. So write and balance the reaction first, and then you have here. You have how you need to calculate. You need to follow the equation, but when you will write and balance, you know that what you need, the value. Like for the breaking here, see, you need this one. For hydrogen breaking, you need this one. When this compound is forming, you need nitrogen 2,2. So here will be some bond. 5, nitrogen 5, correct? So I think like that. Let's see. Oh, no, we will have maybe, okay. Yeah, 3, 2. I think like that. So you need to take the bond. So when you will take and just go for here, you will find the answer. Yeah, see, we will find the answer is here. Another, consider the reaction of for the formation of water. So same, we have to know that how many bond is here breaking and how many bond are forming. So when you will do the calculation, this is the answer, but you will find it here, the details. And this practice question, as I said, that I'm keeping you guys, please practice it, because maybe I'm not going to give the 100% same, but similar. Since this is your 1 month semester, that's why I'm not doing too much experiment. I normally don't do too much experiment with these students. So, because our job to clear the syllabus. I think this is the teacher's job, that according to the syllabus, they will explain or clear the topic to students, and the student's job to do their homework and exam, right? I think this is the simple thing, and I believe on that. I don't go beyond that. So, Let's think like that here. Based on the del H value, the following reaction. Okay, so here ethyl alcohol, liquid. In that moment, you don't need to know all the compound name. This is your basic chemistry. You just need to follow what you need to do. So this compound liquid combined with the oxygen are reacting to produce the carbon dioxide and water. So what is happened, because we give here the negative value. So this one must be exothermic and the heat will be released if it is exothermic. Yeah, exothermic and heat was released by the system. So please practice those questions at the home, and it will also be maybe helpful for your homework. So see, we finished the 6th chapter. I don't think I give you stress. Yeah. Yeah. So please practice it. And if you have any question, let me know. I'm not going to start anything. We have the tomorrow, the periodic trend. But now I will take the question. I mean, if you have any question or, yeah, today we little bit of finish early. As I said, the initially,